Okay, good. Um, Good afternoon, everyone. I'm very glad to have this opportunity to share our work on ZFS here today. And my topic is run ZFS in Userland. My name is Huang. I am a software engineer from LMesh, a company in China, focusing on building cloud-native storage system for stateful applications. And I'm working on distributed storage system and for several years. And actually, I was involved in ZFS just a few months ago when we were seeking for a Userland file system that could run in container. So actually, I'm pretty new to this complicated file system. So feel free to correct me if I had any mistake in this talk. Okay, here is the outline of today's talk. For the convenience, I will use the word UZFS, indicating run ZFS in Userland. So firstly, we will talk about the motivation, why to use ZFS. And then we'll take a look at the existing related work on that. And then we'll move on our implementation and to see how our work is different with the existing work. Last, we'll take a we'll talk briefly about the use case of ZFS. So let's address the first question. Why do we need run ZFS in Userland? The first point is that we love ZFS because of many nice features ZFS provides, such as copy on write transaction model, pool storage, snapshot, and so on. So even ZFS is not native in most Linux distributions, but in the virtualization era, the end user they are able to install ZFS kernel module in VM manually because their workload runs in the VM. However, when it comes to the cloud-native era, the situation is changed. The end user, their workload now runs in a container, which is separated with the host. That means the user may not be around to modify the host kernel. So they may not have the ZFS modules in the host kernel side. Actually, this is the key reason that we explore this project. Another point is that along with the popularization of the low latency hardware like NVMe SSDs, the kernel bypass technology becomes more mature. Intel's SPDK provides the Userland NVMe driver, which could achieve 10 times as low latency compared to the kernel's driver, according to Intel's report. So how could workloads running on ZFS enjoy this low latency technology? The answer is just run ZFS in Userland. So it is the high time for us to consider supporting UZFS seriously. Besides of that, there are many other benefits that UZFS could bring in. It is isolated with kernel, so it has smaller failure domain. And it's also easy to integrate into other storage systems. Because right now most of the modern storage systems, they are distributed, and this kind of system runs in Userland as well. And there are also rich tools and libraries in Userland that ZFS could leverage, such as the TC malloc and the G-test framework, and so on. Last but not least, running in Userland make it easy to develop new features, to do the maintain, upgrade, and debug. And particularly for ZFS newbie, one useful thing is that you can use GDB to run ZFS, which is, I think, really helpful. Okay, with that being said, then is there already some existing work on UZFS? The answer is yes, and let's take a look. The first one is the Fuse solution. I think most of us should already know what Fuse is. Actually, there is a ZFS Fuse project about more than 10 years ago. And that project is based on very old ZFS version and no update since 10 years ago. So I think currently it should be in a deprecated state. And there is also an issue named Fuse implementation in the OpenZFS official repo. It is actually a quite early issue. It is still in open state, starting from 2010. So actually, right now, we don't have a really workable field solution for ZFS in Linux. Another work is the SysStore from OpenEBS. SysStore support running Zemo in Userland, and it could receive I/O and control command from network. But the limitation of SysStore is that it only supports Zemo and not support the file system's semantics. And it is based a relatively old version of ZFS, which released 4 years ago, and it's not upstreamed. But the good thing is that there are a bunch of adopters in their list, which prove that running Zemo in Userland works well in production environment. Okay, so how about this UZFS work? Actually, we have two goals for this project. The first one is that we need to support file system semantics in Userland. So it is easy to integrate with other components like Fuse and application on the server. The second goal for us is that to make it easy to upstream. And our work is based on a pretty new ZFS release that released June this year. And we're planning to use the incremental approach to make a change and make it easy to for review to emerge. Okay, so we'll talk about our implementation. Before that, let's take a look at the current ZFS stack. Look at this diagram. Um, Actually, in the middle is the Linux kernel ZFS. And the core logic of ZFS is under VFS, which means ZFS is running in the kernel mode. And ZFS also provides some libraries and some command line utilities to do the management work, like the zpool or ZFS tool. They call APIs provided by the libZFS for like creating or destroying for ZFS. And this library talks to the ZFS kernel module through this L control interface. And when a ZFS dataset is mounted on the user application, they could use the standard read and write APIs provided by the VFS to access the file system. So let's focus on the ZFS kernel module. Actually, ZFS kernel module has many components, just like the CPL 0, DMU, SPA, ZP0, and so on. But in the story of UZFS, actually, these components fall into two categories. The first one is a gray box, including DMU, SPA, ZP0, and so on. And this layer provides the core functionalities of ZFS on the dataset level. And the other one is the red boxes, including ZPL and ZIMO. And both of them are attached to the kernel VFS layer. They are responsible for mapping a dataset to a file system or a dataset to a block device. And the reason of this classification is actually pretty simple, because these components in the green box are already supported running in Userland, while the ones in the red box have not yet been supported. So let's take a look at this diagram, which shows how current UZFS runs. The core important component is the libzpool, which are including the DMU-SPA and the components in this green box. And ZDB and Ztest are this kind of utility linked to libzpool to do their work, like dump some information of an object or do the test work. Then, how does these components in green box run in Userland? Actually, libzpool add a kernel emulation layer. So for each kernel API, this kind of components use the kernel emulation will use a Userland API that has the same semantics. For example, when issue an I/O, in the kernel side, it will invoke the summit EIO kernel API to issue an I/O to the block layer in kernel. Well, in the Userland side, libzpool, it will call pread, PO, PWrite to a file, which is the backend of the device for the I/O request. So this is the current ZFS stack. And the work of CStore we mentioned before is they putting this symbol into libzpool to make it run in Userland. And what we will do is putting CPL into libzpool, so that libzpool could have the facility semantics. Okay. So let's take a deep look at GPL. A GPL means ZFS POSIX layer. It involves many POSIX-defined concepts such as fire, inode, density, and that kind of thing. But in this story, we also can classify the GPL into two layers, the high-level layer and low-level layer, and just as shown in this diagram. The high-level layer is responsible for implementing the VFS codecs. Thus, it uses the structures defined in kernel, such as the density, inode, file, superblock, and even KLCB, things like that. As a result, each layer is coupled with kernel deeply, and it is pretty difficult to port into Userland. Where the low-level layer actually has a similar interfaces with the high-level, but it is isolated with most of the kernel API. Instead, it uses the low-level structure that's defined by ZFS itself. And we will take an example in the next slide. And actually, the real work of the VFS operations is done in this layer by invoking the interfaces the KME or other ZFS components provide. So the main work of porting BPL into Userland is we need to replace the kernel APIs with the Userland API. Well, since we don't have a Userland VFS working similar with the kernel VFS, so actually there's no need to port the high-level layer. And so our scope is just porting this low-level layer into the Userland, which is the two yellow boxes in the diagram. And currently, ZFS has already done some abstraction of this GPL low-level things. It separates this kind of files into like OS specific and some common functionality. And for this common functionality, they are not involved. They don't involve the like the kernel API. So these files are pretty easy to port into Userland. So the major work is to put in these OS specific files into the Userland. Okay, so here is the example to show the high level and the low level APIs in ZPL. The operation is make direction. And this one, ZPL underscore make direction. This is actually a high level API. And it just implements the VFS make direction codec. Thus, it used this kind of the structures as their parameters. And ZFS underscore make direction is actually low-level API, and it uses like Z-node or a chain as the parameters. And the high-level ZPL underscore make direction is firstly translate this inode to Z-node and dng to the chain. And then it will call ZFS underscore make direction to do the real work. And the low-level API will invoke like this kind of functions that's provided by the ZFS core component. So yeah, after the scope is determined, how do we do it? But the next question is how to organize the code. Basically, there are two options. Option one is copy all the low-level GPL code into a separate direction, and we do the change replacement there. But obviously, the good thing is that there is no impact on the existing kernel code. The con is we are bringing lots of duplicate code, and this will obviously increase maintenance cost. Option two is we reuse the kernel code and we add some if-defined macro in the kernel code. Like if defined kernel, we call this kernel API, else we call the Userland API. And we need also add the kernel emulations, which just like the current ZQ does for the DMU layer. Also, the pros is that we can reuse the kernel code and add minimum new code for it. But the cons is that there will be many if-defined in the kernel code. And actually, currently we use the option two, but I think this may need to be discussed further. Like if we it could refactoring the current CPL code to use a more generic way to code the platform-specific logic. But this is just an open question. Okay, so using this approach, we could build all the low-level ZFS the GPL code into the ZQ. And after putting GPL into libzq, we also provide a separate library named libuzfs, which provides APIs for app layer to use. This kind of API, it is actually just a wrapper, and make it very easy to integrate at the app layer. So take the make directory, for example, like the FSID refers to a dataset, and DN number refers to the directory inode number, and the name is the entry name, and the new created inode number is stored in the last element. So using this style APIs can make it pretty easy to integrate with the Fuse and the Ganesh NFS backend, because they also use this style in their codec. So using ZFS, we implemented a basic version of ZFS Fuse, which supports mounting through the Fuse kernel module. And translated from the ZFS API, it's really easy to integrate with Fuse. Here is the example. So this is the Fuse callback to do the get attribute operations. And we can see that the call thing is we just need to call libuzf get attribute API to do almost all the work there. And so regarding this ZFS fields, currently we supported these operations. They are really basic operations for metadata and for I/O. A limitation here now is that the management command is not supported yet, so we cannot do like set property or get property thing, and we still cannot do the create a ZPool or destroy the ZPool, things like that. Well, besides ZFS fields, we also implemented some other command line tools. The first one is UserFS tool. This is actually just used to test the UserFS functionality and do the performance upper limit, because this tool is linked to the UserFS and the zip directory, and all the code are running in the same process. So there is no communication between process. So it could use to test the performance up limit. And to manage the UserFS, we also let ZPool and ZFS tool link into a libZPool, so that we can do the basic management operation, such as create or destroy the ZFS and get set the property. But the limitation is that if you use ZFS fields, you cannot do this kind of things when the dataset is mounted, because currently we have support that. Okay, so here is the whole picture of the dev stack after our work. And what we do is that we add these three yellow boxes into the ZFS stack. The GPL is added to make libZPool supports file system semantics, and libUserFS provides easy to use APIs, and this command line tool to do actually the real work. Okay, so here is the performance data we currently have. And one thing I want to emphasize is that since currently we are still working on the functionality side, so we haven't done any performance tuning work yet. So this data is not that meaningful, except for just indicate the current baseline of the UZFS. So here is the metadata operation, OPS. We tested 3 scenarios with empty text, the kernel ZFS, the UZF tool, and ZFS fields. And the operations is the directory create, state, remove, and the operations for create file, state file, and remove file. Well, empty text is a common benchmark for file system metadata. We just use one slide, and the file number or disk number is 1 million. And we in this test we drop the VFS cache before each operation test. We can see that ZFS fields has big degradation compared with kernel ZFS or UserFS. And the data just like around 5,000 at that level. And I think this actually it's understandable because there are additional requests between kernel and userland when we're using the fields. For example, for a state file, we observe that there are 3 lookup operations and 1 get attribute. And if using in the kernel side, that should be okay. It will be quick, but in the fields, there are many back and forth communication between kernel and userland. Well, a good thing is that the ZFS has rough practice with the kernel ZFS, especially for the create operation. But like the remove operation, still have some degradation. But so far, actually, we don't do the further research on that. Why had this kind of degradation? Okay, so this is the bandwidth data, and we use FIO to test the sequential read and write on just one file, and the ZFS fields it could achieve like more than 300 megabytes per second for sequential read, and 250 for sequential write. And compared with the kernel ZFS, it still has a big degradation there. And the common reason is that it obviously needs axial data copy between kernel and the user. So as I said before, so this data it actually just indicate what is the level, what level currently we could get with the fields. Okay, so let's talk about the use case of UserFS. Typically, there are 3 typical use cases for UserFS. The first one is pretty straightforward. With ZFS fields, a container can use ZFS even when the host kernel doesn't install the ZFS module. The second one is that we can integrate it with connection unlike server, which runs in the userland. And you just use the ZFS as a backend storage engine so that you can provide the NFS service, especially when you are running it in container. And the third one is use ZFS to build a cognitive distributed data system. Typically, distributed file system need provide the HA capability, which means if one server crashes, the storage should be rebooted quickly to provide service. Well, ZFS doesn't need the FSCK after power outage, which is a key feature in this scenario. Because if we use other file system which need FSCK after crash, because FSCK may take long time after power outage. So in that case, the workload will be impacted. So for ZFS, this is a really good thing. Okay. So here is the current status of our project. Basically, this project is still under development. Here is our developed repo on GitHub. And currently the basic file operations and I/O works. There are still lots of work to do. Here the feature work. The first one is that we will create PR to the upstream do some more refactoring code work for further discussion, such as how to organize the code for the userland. And for support more features, because currently we did some fake kernel emulation, which caused some features not work, like the snapshot, the extended attribute quota statistics, and so on. So we need to support them further. Regarding the ZFS fields, the most important thing is that it should be support the zip or ZFS command line utility. And another limitation is that currently it only supports one thread mode. So multi-threaded mode should be supported as well. And for the longer term work, we need to add a new like SDK and NVMe with the tab to integrate with SDK, because currently Liquid could use the period of period to access the file type with that, which is inefficient. So at least we need to seek async I/O model. Okay, so actually here is the key takeaway of this talk. UserFS is desired in the modern cloud-native era, and UserFS is doable, and UserFS creates more possibilities. Okay, that's all of my talk. Thank you. And I can take questions.
So it seems like this was heavily focused on Linux Userland. Is there a possibility for future work on previously?
Can you hear?
If I hear correctly, the question is, this is only for Linux, and it work for FreeBSD. Is that the question?
Yeah, that's the question.
Okay. Actually, no. We because we don't support FreeBSD right now, because actually our use case is only for Linux.
So does this work as a Userland daemon that you connect to, or it works in memory address of the process using the Userland ZFS?
The question, does it work as a Userland daemon, or does it work as kind of in the Userland processes memory space? Is that yeah? Did you hear that there?
Oh, okay. If you use the fields, ZFS fields, actually it works as a daemon. But actually, the core functionality is the frequent UserFS, that you can do more development to integrate that library into different storage system. Like we just integrate it into the fields so that you can have the fields functionality. You can also integrate with the conventional NFS server so you can actually build a finished NFS server there, and actually the NFS server is also run as a server or as a daemon.
The libUZFS API that you're using with Fuse is stateless, where you, instead of having pointers to structures like a data set or whatever, you're using uint equal to T. And that doesn't really strike me as being particularly great for performance, because you're going to have to look up the data set from some structure or whatever every single time you do an operation. Why did you go for that design choice?
You mean the FSID is 640?
It's a uint.
Yeah.
With some structure in memory.
Yes. Well, the reason we use the 614 is like it actually it is like the the current the ZFS it could use 64 kind of things. So we here actually we don't have a particular situation on that because one thing that when we built like a distributed file system, it is limited, has the limitation on the app limitation of the FS. You can create it, and but maybe 32. You in 32 is also good enough. But right now, actually, we don't have a special consideration on that. We just like what ZFS use.
I think the question is like, why is it stateless? Like, why for the FSID you're taking like a number that's the file system as opposed to a handle that some other routine would open and then you pass to the maker. You know what I mean? I think the interface has to do with like the interface that's coming into you, where like over NFS, you're getting an SSID or you're getting versus are you getting a pointer?
Yes, like this. This FS initiate function, it just translates FS name into FS ID. Well, this FS ID is created by UserFS itself.
So I actually took a peek at the pull request a couple months ago, as someone mentioned it to me, and something that stood out to me was that instead of using the IOCTO interface, you are using a named pipe, like ZFS Fuse did. That strikes me as being very difficult to maintain versus, say, using CRUISE, which is character device and user space. Did you specifically choose that over character device and user space, or have you? What kind of thought have you put into this?
Sorry, I didn't capture the question clearly.
So the management interface for the kernel modules uses an IOCTO interface. So IOCTO. And for your pull request, you have changed the management interface to use a pipe.
Pipe? You mean the ZFS Fuse implementation?
Yes, like the original ZFS Fuse implementation. There's something called character device and user space where you could implement the IOCTO interface, with the exception of sensors and need to use a proxy. But I'm just curious, why did you decide to use a pipe over re-implementing the IOCTO interface and user space using character device and user space?
Do you ask the control path of the ZFS fields monument because I know that there is a CUSE which expose a character directory device so that you can talk that character device for the virtual path. And currently we haven't because we haven't support that virtual path. So we don't use that right now. But when if we need to support that control path, actually this CUSE solution will be the option for that.
Okay.
Right, I have two questions. One of them is, what did you use to write to disk? Is it just like a normal write and read system call? I saw there was some future work about using SPDK.
So the question is, how do we write to disk? Is it a normal read and write call? Did you mention the SPDK API?
You mean the SPDK API?
Yeah, but what do you use today? Is it normal reads and writes to writing to disk?
Actually, right now we don't support SPDK API. It is currently a future work, but we do some prototype using SPDK NVMe driver. That actually this could be done. If you integrate with the SPDK NVMe driver, you can we just abstract I/O engine for that and use the interfaces that the lib SPDK NVMe provide to issue the I/O to the real NVMe disk device. And then they provide async I/O model for that. So right now the ZFS haven't integrated that, but in the longer term we'll do that.
So today is it just normal P reads and P writes?
Yes, today the current implementation is we just use the P read and P write. And one thing, one more thing is that the 604, they already support the lib AI async IO model using lib AIO, and they have already implemented such implementation in Userland. But right now we haven't integrated that yet.
Anybody else?
This is a follow-up to that question.
Sorry for that.
I actually recall.
Actually, we don't notice that. You mean? Ah. Okay, actually, we haven't noticed that. Thank you for raising this point. We can check that offline. But yeah, that may have an impact on the performance.
Any other questions?
Thank you, everyone.